Hi, welcome back. You've been reading about displacement, velocity, and acceleration. Still very straightforward. Let's look at those three concepts really quickly. Displacement is a vector, it has a direction to it. Displacement is just change in position of an object. We use the symbol delta x to indicate that it's x2 minus x1, or x final minus x initial, if we're written that way. The delta x is not delta times x. This is meant to be one quantity. Delta x is one thing, it's the displacement. So again, it's a vector. If you go to the right, it can be positive, to the left, negative. If you go up, positive, down, negative. Your book does a good job of describing this, pointing out, for example, if you've got minus 1, 0, 1, 2, 3, even if you take a very long path, if I start at 1 and go over here, and back over here, and then back over here, and end up here at 3, my displacement is still just plus 2, even though I may have traveled a great deal of distance. My displacement is still delta x. It's just x2 minus x1. It's just 3 meters minus 1 meter is 2 meters. Because displacement just has to do with the final position minus the initial position, not the path in between. Okay. Velocity, or more strictly at the moment, average velocity. So V average is x2 minus x1, that's displacement, over t2 minus t1, or we could write that x2 minus x1 could be written as our delta x, t2 minus t1 could be written as delta t, change in position over change in time. Anytime in physics we divide by change in time or elapsed time, we think of that as a rate of change of something. So this is the rate of change of what? Position. So our average velocity we can define as the average rate of change of position. And so there will be many cases throughout this course where we have definitions that are rates of changes of something. We'll see another one before this little mini lecture is over. So this is our average velocity. Now this could even look familiar to us if we were to do a plot of position x versus time t, and if we had a particle start at some x1 at some time t1 and move to some position x2 at some later time t2, notice the following. This distance is x2 minus x1 is delta x. This distance is t2 minus t1 is delta t. So delta x over delta t is just the slope of that graph, and we see the slope just of a position versus time graph gives us velocity. Now later we'll talk very specifically about a little more, not specifically, we'll talk a little more about slope of position versus time graph later in the chapter. Another way of thinking about this, we've got V average is delta x over delta t. If I multiply through by delta t, I get delta x is V average delta t. Delta x we can just think of as distance is velocity times time. And you see this just says, this definition of average velocity just says the distance is just velocity times time. That is, if you travel 50 miles an hour for 2 hours, you'll go 100 miles. It's really quite that simple. Next week we'll get more challenging. Now, a slightly more subtle concept is the concept of acceleration, or at the moment, average acceleration. So acceleration average is V2 minus V1 over T2 minus T1, or we could write that as delta V over delta T. Again, we're dividing by change in time or elapsed time. So that's again a rate of change of something. Rate of change of what? Velocity. So our definition of average acceleration is rate of change of velocity. Or more specifically, since I'm talking about average, I should have said it's the average rate of change of velocity. Whereas instantaneous acceleration would be that change at a particular instant. This was the average rate of change of velocity. Your book talks about that. Now, what does this mean? Well, suppose we have an acceleration of 10 meters per second every second, or we would write that as 10 meters per second squared. This would mean an increase in velocity of 10 meters per second every second. So something experiencing this acceleration would get faster at 10 meters per second every second. So after 1 second, it'd be going 10 meters a second. After 2 seconds, 20 meters a second. After 3 seconds, 30 meters a second. After 4 seconds, 40 meters a second. This is how fast the velocity is changing. And with this positive acceleration, the velocity is increasing, and if plus is to the right, it'd be increasing to the right. Now, acceleration does have some subtleties to it, some subtleties to the direction. Let's think about that for a moment. Suppose I have a car, and that car is going to the right. I didn't really draw it, it looks a lot like a car going to the right, but it's going to the right. And let's suppose that car is going to the right, and it has a positive acceleration. That car will be speeding up. Now suppose that car is going to the right, and it had a negative acceleration. So it'd be going to the right, but with a negative acceleration, that car would be slowing down. And eventually would come to a stop, and if the acceleration continued, it would start speeding up the other way. Now suppose that car had been not going to the right, but had been initially going to the left. Now going to the left, if it had a negative acceleration, it would be speeding up. Negative, pointing to the left, it'd be getting faster and faster to the left. If it had a positive acceleration, suppose it's already going to the left, but it had a positive acceleration, that would mean it was going to the left, but slowing down. And eventually it would come to a stop and speed up and go the other way. So there are these subtleties to the signs and the directions of acceleration. You'll practice that a little bit in your homework assignment. So be sure you understand those directions, and ask me or ask one of your learning assistants if you don't quite get it. So just a quick example, just a numerical example of an acceleration that I looked up. Some of you might enjoy cars. I looked up an example of a Dodge Charger that you might consider a muscle car. A Dodge Charger can go from 0 to 60 miles per hour in 6.4 seconds. So it can change its velocity from 0 miles per hour to 60 miles per hour in an elapsed time of 6.4 seconds. So that's acceleration information. Let's compute its acceleration. Now we know how to convert from miles per hour to meters per second, but I've already got it here. 60 miles per hour is 26.8 meters per second, just to save us a few moments of time. So our average acceleration for this Dodge Charger is V2 minus V1 over T2 minus T1 is 26.8 meters per second minus 0 meters per second over 6.4 seconds minus 0 seconds. So I've got meters per second. Every second, that's supposed to be a second. So 26 8 divided by 6.4. This is 4.19 meters per second every second, which we write as meters per second squared. So the average acceleration of a Dodge Charger is 4.19 meters per second squared. That's how rapidly its speed can change. So if we just call that a 4, after 1 second it'd be going 4 meters a second, after 2 it'd be going 8, after 3 it'd be going 12, after 4 it'd be going 16, after 5 it'd be going 20. Get the idea? That's how rapidly it can change its velocity. So you can now practice that with your homework, and I will see you soon.